Hi everyone. Good morning or good evening, depending on where you are. And welcome to day 2 of Pulsar Summit Asia 2020. And hope you have enjoyed all your talks yesterday. And my name is Sijie Guo. I'm one of the PMC members of Pulsar and Bookkeeper. I'm also the co-founder and CEO of Stream-Native. And today I'm going to share like function mesh complex streaming jobs in a simple way. So originally that my coworker Neng is going to give the presentation. However, he's not able to attend this conference today. So I will just give the presentation for him. And as you have known, Pulsar provide different mechanisms to do data processing. And Pulsar integrates Presto for interactive queries, and it integrates with data processing engines like Spark and Flink for unified batch and stream processing. And besides them, Pulsar also provides a serverless lightweight event streaming framework called Pulsar Functions for serverless event streaming. So for people who is not very familiar with Pulsar Functions, let me use a couple of slides to give a brief introduction of Pulsar Functions. So Pulsar Functions was designed for simplicity. So that this diagram shows the basic elements for a Pulsar function. A Pulsar function can read the input messages from multiple input topics, apply a processing logic, and the result returned by these processing logic will be written as output messages to the output topic. And Pulsar function also provide a built-in state for state management, and providing a mechanism for Pulsar functions to be able to manage in mutate state. Also, you can write log messages and to a log topic for troubleshooting any issues on production. And as you can see from this diagram, Pulsar functions that you focus on writing your own business logic, and the function runtime on setting up consumers on reading messages from the input topic, setting up producers to write the messages to the output topic, and as well as managing the state in Bookkeeper for the application and ensure different processing semantics. I would like to kind of clarify what is and what is not for Pulsar functions. So Pulsar function is not yet another full power data processing engine. It's also not a new computation abstraction layer. Pulsar function, you can think of Pulsar functions is Lambda style functions that are specifically designed for serverless event streaming with Pulsar. And it can be used for about like 80% of use cases. Most of the use cases are lightweight computation use cases like ETL jobs, real-time aggregations. You can use Pulsar functions for building microservices, reactive services, or do event routing. And the whole API is also very simple. It's language native. That means you don't need to learn extra SDK in order to write streaming applications using Pulsar function. And if you know how to write Java, Python, Go, then you know how to write a streaming application using Pulsar function. So this diagram on the right shows the kind of a simple business example. And the code examples in the left shows how to write this business logic using different languages. Like if you just take a closer look, and this is the Java function, and this is the Go function, and this is the Python function. As you can see here, it's entirely language native. There's no much difference as you write normal applications. So as Pulsar functions is a serverless event streaming framework. It also provides kind of different data processing semantics for from most one's processing semantic, it is one's processing semantic to effective one's processing semantic. And by default, all of our functions you submit is running in at least once mode. So the difference between different semantics, it really depends on when you acknowledge the messages back to Pulsar. For most ones, the message is acknowledged back to Pulsar once Pulsar function receives the message, but before the function is actually executed. And for at least once semantic, message is acknowledged to Pulsar only after a function is fully executed. And effective ones is the Pulsar achieve effective one's semantic is through its idempotent producer. So the effective ones is actually very limited. It only limited to a function reading from one input topic and writing the result to one output topic. You are not able to do effective ones across multiple topic partitions. In Pulsar 2.7.0 release, we introduced Pulsar transactions. We are going to fully integrate Pulsar transactions into Pulsar functions in order to provide a transactional event streaming semantic in Pulsar functions. So then you are able to achieve effective ones across multiple partitions. And Pulsar also provides a built-in state management. Application can use a context object to access and mutate the state. And the state, right now the state is managed and stored in Bookkeeper. In the future, we are going to make the state storage pluggable. And that means that you are able to use the familiar storage system as a state in Pulsar functions. And this is a simple example, word count example that everyone would learn when you learning data processing engine or learning a streaming framework. The first thing you will do is word count. And as you can see here, writing a word count is very simple. You just need to take the input and split the input into multiple words, and using the method provided by the context to increment a counter for individual word. So it's very simple. All of complexity is managed by Pulsar functions. And as I mentioned before, Pulsar is an API-driven system. So all the resources in Pulsar are actually through this RESTful administration API. Same applies for Pulsar functions. All the function API is actually exposed to through Pulsar admin RESTful API. So you can use Pulsar admin tools to interact with Pulsar for managing and operating those functions running in a Pulsar cluster. And Pulsar functions not actually provide a very flexible runtime in deployment mode. So it supports different language runtimes. You can write Pulsar functions using Java, Go, Python, and more is coming. And Pulsar broker or function worker is actually can run a function using different threading model. You can run Pulsar can run functions as a thread for Java language, and it can run function as a separate process for almost every language that's supported by Pulsar. And besides that, Pulsar functions also support different deployment model. You can co-run the functions together with the broker. And if you care about isolation, you can set up a dedicated function worker cluster and run the functions in that dedicated function worker. But if you are moving towards a cloud-native infrastructure, you are using Kubernetes as the fundamental scheduler. Pulsar also provides integration with Kubernetes. You can easily configure Pulsar functions to run on Kubernetes. So as to put all this together, Pulsar functions actually provide a simple API to use to improve the developer productivity. And it's fully integrated with Apache Pulsar, so no extra system or service setup needed. And it's easy to operate. Also, it provides a lot of tools like local runtime, log topics for easy troubleshooting. So it's a very easy to use system. And I would say Pulsar function is one of the main factor driving the adoption, or driving the growth of the adoption of Pulsar. And as I mentioned before, Pulsar has a very deep integration with Kubernetes. You can run Pulsar on Kubernetes, and also let Pulsar schedule Pulsar functions on as parts in Kubernetes. And this is a diagram showing how Pulsar schedules functions on Kubernetes. So a user that who want to create a function, it would first talk to the broker, and within the broker, a module called function worker, and the function worker would take the request sent from the user. It's a create function request, and the function worker would first write the function metadata into a function metadata topic. It's a Pulsar topic. Function worker use Pulsar topic as for its metadata management. And there's leader elect across multiple brokers, and the leader would examine the Pulsar metadata topic, and also check what are the function workers available in the cluster, and you will calculate an assigned map, and then we'll publish the assigned map to an assignment topic, and every function worker will just tell the assignment topic, and each worker will receive a portion of the functions. And when the worker receives the portion of functions, it would talk to Kubernetes API and create a stateful set for individual functions. So it's very easy, but it's also the function worker need to implement a lot of logic to talk to Kubernetes and managing the state and thinking the metadata information stored in Pulsar topic to Kubernetes and make sure it create a right stateful set. This is a kind of great starting point, and a lot of people is actually deploying using Kubernetes in also deploying Pulsar functions using Kubernetes on production. However, the approach have a couple of problems that we are facing. First, the approach is not a Kubernetes-native approach. And that would usually introduce a problem when you run Pulsar and Pulsar functions on Kubernetes is the broker crash loop. The problem of a broker crash loop is there's a tricky dependency between the function worker and broker. So when you run function worker as part of broker, the function work depends on certain number of topics for Pulsar function metadata management, and that metadata management need to wait until the topic become ready. But the broker would claim itself to become ready is when all the components are started. Like you need to make sure function worker is started. So it's a kind of a weird dependency between function worker, metadata topic, and the broker, and that it usually take a couple runs for a broker to restart until it reach a certain state. So if you deploy functions and brokers, function workers on Kubernetes, don't be surprised about this broker crash loop. And we have been spend time on improving the process, but it's not a very nature behavior when you run Kubernetes on run Pulsar on Kubernetes. The second problem, the second one is, as you can see here, we store all the function metadata in Pulsar topics, and when we create a job for running the functions, we create a stateful set on Kubernetes. This duplicate function metadata. So it would become very tricky and really hard to make sure these two state is in sync. For example, like a common behavior is like some people kind of create a cluster on Kubernetes. They want to test out all the functionalities, but when they test out all the functions, and they would kill or delete the cluster, but it will let all the stateful set keep running on the Kubernetes clusters, because you are now able to kind of automatically delete all those stateful sets. And the other way around is because it's a Kubernetes stateful set, that means you can use any Kubernetes tools to delete the stateful set without changing the metadata. So it will cause inconsistency between the metadata stored in Pulsar and the metadata stored in Kubernetes. And the last one is because the implementation of current Kubernetes integration is not leveraging a lot of, it's not a Kubernetes-native approach, so it doesn't leverage all the tools provided by Kubernetes ecosystem. And it's hard to implement features like even like Kubernetes already have autoscaler in place. It's really hard to kind of put that logic into Pulsar in order to leverage that functionality. I mean, I don't say it's not possible, but I just say it's hard. And the functions are also kind of the second problem that leads into a second problem is the function are tied to a specific Pulsar cluster, and it's really hard for to use functions across multiple Pulsar clusters. Let me just give you an example. So that example is a Federated Learning. So in a Federated Learning setup, you usually have multiple Pulsar clusters that each cluster might belong to different organizations, and you cannot directly access the topics on different clusters. So you have to set up a kind of a centralized cluster that it is able to run functions, and that functions would talk to individual cluster to moving the data to receive the data from one cluster and write the data to the other cluster, to be able to achieve the business goal for federated learning. But in that case, then the function itself doesn't belong to individual cluster. In order to run these functions, you have to set up a Pulsar cluster in order to do that. And that Pulsar cluster only just for storing the metadata, which doesn't seems to be a good approach, because you're already on Kubernetes, you already operating the Kubernetes infrastructure. Why can't we just run functions natively on Kubernetes and allow the function is able to talk to cluster A and write the data to cluster B? And that was the kind of the second problem we see with the current setup on Kubernetes. And the last one is actually leading into our main topic is it's really hard to build a complicated streaming job with multiple functions. The reason is you can do that, but it's not nature way. For example, if I have a business logic that need to be written using 6 functions, and what you have to do now is you have to create individual functions. And for these individual functions, you need to run function create. And if you want to update, you need to run functions update for all 6 functions. A potential, if you want to scale up, you need to scale individual functions. So it's a lot of redundant work you need to do in order to create a streaming job using multiple functions. And it's also hard to check all the functions as an integrity, because those functions are just individual functions, so you can easily kill a function, and that would lead into that a function is not running. And also, it's really difficult to know what are the upstream and downstream functions for a given function. So it's really hard to figure out the whole dependency graph between those functions. So that leads us into thinking about, well, can we build a framework that is allow people to write streaming applications using multiple functions? And that leads into our thoughts about function mesh. And we submit the PEEP. The idea of function mesh is basically combine a collection of functions So those functions can collaborate together to achieve one final data processing goal with a clear defined stage. But I want to also clarify the goal, the way how we think about function mesh is not designed to be a full power data processing engine. It just want to simplify the Pulsar function users to make their life much easier, so that you can use function mesh to combine multiple functions together. And Pulsar function mesh is able to manage all the function as an integrity. So you don't need to kind of create individual functions and chain the function together through topics. And this is just a simple diagram about a function mesh that you have 6 functions, and individual functions connect through a Pulsar topic. And so once we have this idea and the goal, we submit the PIP called PIP 66. The original idea is, okay, then let's implement this Pulsar-Native function mesh in using the current framework. So that leads into our initial implementation, that is implement that based on the existing Pulsar function framework. So for people who might already know about function, from function endpoint, function topic, those are to the right. Those are the components that already exist in Pulsar functions. So the function endpoint take the inputs for all the function RESTful API, and the function endpoint will write all the function metadata into a function topic. And the function topic would be tailed by the leader and to receive all the function metadata. And it will calculate an assignment map and publish the assignment to assignment topic. And each function worker would just tail the assignment topic, and individual worker would receive a portion of the functions, and they would execute the functions based on the select runtime. So our original idea is, okay, we already have this framework. Then the easy way is just like introduce a mesh endpoint and introduce a mesh topic for managing all the metadata of function meshes. And one, you can just introduce a mesh metadata manager, and it would just tail all the mesh metadata and then convert the mesh into individual topics. So it's an easy approach, and we actually have a prototype implemented, and it ran well. But we quickly realized it doesn't really solve the problem. It actually makes the implementation much complicated, because it can solve the mesh problem, but it doesn't solve the problem that we have seen in when running Pulsar on Kubernetes. So we kind of step back and think about if we want to make Pulsar function really successful on Kubernetes, on cloud native ecosystem, then we may need to kind of adjust our thoughts here. Is can we just create function succinct and also the mesh as a CRD that for people who don't know CRD, is a Kubernetes customer resource definition. So you can customize any type of resources. And the idea is maybe we can just create function succinct mesh as a CRD in Kubernetes, and we can just write a function mesh controller. The controller would just watch the CRD, and it would just do the scheduling and to schedule individual functions, sources, things, and even meshes to Kubernetes. And that is a natural way to integrate all the full power scheduling capability provided by Kubernetes. So you don't need really to write any customized code to talk to Kubernetes API in order to do that. So that is kind of the thoughts process behind that. And we kind of change a bit our design. Is we introduce the CRDs, and now you can just talk directly to Kubernetes API. Like you can create a function YAML file source YAML file and sync YAML file and mesh YAML file and as a CRD. And once you create a CRD, the mesh controller would receive the CRD from Kubernetes service, and it will schedule individual pods, and the pods would just talk to Pulsar. And the benefits of this approach is your metadata is actually stored directly on Kubernetes API server, and as well as your running state is also on your Kubernetes server. So it's a consistent state. You don't it would solve the problem you see that you store the metadata on Pulsar topics, but you store the running state on Kubernetes. So we introduced kind of four type of CRDs. That is function, source, and thing. Let me just like walk you through one by one. So this is just actually I'm not sure if you are able to see that, but as you can see here, the YAML file is very similar as a function config, and the only difference is the CRD should be written in Kubernetes kind of API format. You need to define the function as a kind, and you need to specify what which namespace, which Kubernetes namespace you want to run these functions. But otherwise, then you would get almost exactly the same settings as you can get from the function config. But I want to highlight a couple of differences here is here is the replicas in Max replicas. Max replica is a concept, it's typically a concept in Kubernetes world. And in this, you can think about it's a function instance. So you want to run these functions as one instance. And max replica is actually what is the max number of the instance you want to run for this function. So in this example, the minimum replica would be 1, a maximum replica would be 5. That means the function mesh controller would automatically scaling up the functions up to 5 instances. And you don't really need to kind of managing like how many instances you really need to run. Right now, the auto-scaling mechanism is based on the CPU usage. But in the future, we are going to use backlog information for scaling up and scaling down. And the second one I want to highlight is the secrets. So if you have been used Kubernetes before, you know Kubernetes provides a very comprehensive secret system. You can just define your credential as a secret in Kubernetes. And in Pulsar Functions, we actually provide the secrets API for you to access the secrets. And in this function mesh runtime, we actually just leverage Kubernetes secrets. So you can, in your function config, you can just reference Kubernetes secrets. You don't need to really store the credential in the function config file. That would improve the whole security for your functions. And the last one I want to highlight here is in the function CRD, you can define which cluster you are referencing for this function. For example, in this example it's referencing the test Pulsar as a cluster, and test Pulsar is actually defined as a config map. We didn't create a separate CRD for Pulsar cluster yet, but in the future we might define a Pulsar cluster CRD in order to kind of make all the resource management much easier. But for now, you can define a Pulsar cluster as a config map. Let's say if you have 2 clusters, you can define 2 config map. Individual config map just store the configuration for that cluster. And in the function, you can just reference which cluster you want to use. So this would allow you run a function that is able to talk to different cluster. So that is kind of a difference for function mesh. So for function CRD comparing to a raw function config. Similarly, we define the type for source, and it's very similar as functions, but the difference is in the source, you will see source config, and that is the one that would fit into a source. Same thing as think, that is you're able to kind of define a CRD called think, and you're able to provide the think configuration. And the last one I want to highlight here is the mesh. So a mesh is just, as I said, for mesh, a mesh is just a collection of functions at this moment. So what you need to do is just write a CRD that is the type is function mesh, and put all the functions that you need to run together as this mesh in the functions list. And once you've done that, the function controller would kind of monitoring the changes of this mesh CRD, and it will automatically scheduling individual functions in making sure these functions exist as a whole, or they will be deleted as a whole. So you don't really need to kind of manage the functions individually. So that is the three different type of CRD we introduced as part of the function mesh. And once you have the CRD, then besides the CRD, that we also do a lot of things that to make sure the function mesh is integrated well with Kubernetes ecosystem. Like as I mentioned, integrate with Kubernetes secrets so that they can read the secrets easily, and leveraging the Kubernetes autoscaler to autoscaling based on CPU usage. In the future, we support autoscaling based on backlog, and utilize the full Kubernetes scheduling power, and allow one function is able to talk to multiple different Pulsar functions. And the last one is we are going to introduce function registry in Pulsar 2.8 for function package management. Once you have the function package management, a function package can be reused by different functions. But as I said, the idea was coming out from implementing function mesh within Pulsar, but we kind of move more closer to Kubernetes ecosystem. But we also want to provide a fully compatibility with Pulsar admin CLI. So if you're already running Pulsar functions using Pulsar admin tools, you don't really need to change the way how you use Pulsar functions. And instead, you can just plug in the function mesh admin API. Then you are able to take all the admin RESTful request. And the only different change here is the broker doesn't talk to metadata topic anymore. The broker will just talk directly to the Kubernetes API server to create the CRD, update the CRD, or delete the CRD. And all the remaining job will be done by the function mesh controller. And that would be a very Kubernetes-native way on doing like scheduling and updates. So this is kind of the idea of introducing function mesh. And I just want to give you a demo, but I realize I only have 5 minutes, so I would probably just skip a couple of demos. And in the future, so I will upload the slides, and everyone is able to check out demos. We have Java function demo, Go function demo, and also MongoDB source and Elasticsearch. And I'll just jump directly to the function mesh. So this is a function mesh example demo. Is in this mesh there are 2 functions. One function is ex1 and the other function is ex2, and the ex1 is reading from input topic called in topic and publish topic to meet topic, and the ex2 will read message from meet topic and write to an output topic called output. And those 2 functions right now are kind of identical. They both add a character at the end of the string. So what you need to run a function mesh is you just need to, actually, let me just skip some of them. So you need to, actually, sorry. First of all, you need to, I'm not sure if you are able to see that, but in this top left corner, the command is doing upload the function just into Pulsar. So then you have one location in the future that this command will be replaced using function registry. And once you upload the function to Pulsar, then the second step is you need to install the function mesh controller. So this it's happening in the bottom left corner. It's building it's building the function mesh controller, and you would install all the CRD required on the Kubernetes environment. And once you install the function mesh controller, then you can use kubectl to apply the function mesh YAML file. And once you apply the function mesh YAML file, Kubernetes would schedule two like function pods for individual functions. So okay, so as you can see here, there are kind of two parts here. The first part is function mesh dash sample dash ex1 dash 0. This is the one part for the first function ex1, and the second one is the part of ex2. So as you can see here, the fundamental, it's very simple. You just need to write a function mesh YAML file, and your controller would automatically do the magic on scheduling the function parts, and you don't need to do extra work. And I will probably skip the verification stage, but I would just show here. Okay, so in the kind of a top right corner, you will see a window that it receives a message called hello function mesh, and you will see two characters are appended at the end of this string, because that is a message flowing from input topic going to the first function to the middle topic, and the middle topic going through the second function and to the final to the output topic. So this is a simple example of function mesh. I have 1 more minute, but I want to kind of show another demo, but I'm not able to do that demo, but I want to kind of show an example that is, you can use Pulsar functions or Pulsar itself, combine Pulsar function to build a real-time streaming machine learning pipelines. So just FYI, recently we contribute TensorFlow IO integration with Pulsar cluster. So right now you can use TensorFlow to read and write data from Pulsar. And now it became very easy is assuming if you are building a streaming machine learning pipeline for car sensor data, you can just enable MOP directly on Pulsar cluster. So you can get all the data directly to Pulsar cluster. Then you can write a Pulsar functions to do ETL. You can clean up the raw data and produce the clean up result to Pulsar, and use TensorFlow to read the data from Pulsar and do the machine learning. And after you have a machine learning model, you want to apply any actions, you can write the data using TensorFlow, write data back to Pulsar cluster, and it can be used for notify your car, and that would be used for applying any machine learning result directly to the subject. So it's a fun project, and the video has like 7 minutes, and I'll probably just give the example in this presentation, and this is kind of the whole talk about function mesh, and I would like to kind of spend 1 minute to think to my coworkers that who has been spending time on design function mesh, and also putting up all the efforts on for running all these demos. And without their hard working, I'm not able to kind of present function mesh in this presentation. And at the end, I would like to thank you everyone for joining my talk. And we are going to open source the whole function mesh work in Q1 2021. And if you're interested in using this feature before that, feel free to reach out to me directly. We are happy to share what we have right now and get initial feedback. And you can also follow us on our GitHub organization. And if you want to discuss Pulsar, you can join Pulsar Slack channel or follow us on Twitter. And thank you, everyone, and hope you have a good rest of the days in Pulsar Summit Asia 2020. Thank you.
Thank you, Sijie. Function Mesh is really a great way to simplify complex streaming jobs. It will surely benefit our Pulsar function users.